Hi friends, welcome to this video on Retrieval-Augmented Generation, or simply RAG. Today we'll go beyond surface level definitions and dig into the actual mechanics that is covering indexes, chunking strategies, embedding logic, and how ranking drives relevance in retrieval workflows. In AI, Retrieval-Augmented Generation, or simply RAG, is a pipeline that improves how language models answer questions by retrieving relevant data first. Here's the typical flow. A user submits a query, then the system embeds the query into vector space. It then retrieves semantically similar chunks from a vector store, which is typically populated offline in a separate process. Then these chunks are ranked for relevance, where the top ones are used to craft a prompt with the retrieved context. This prompt is then fed into a language model to generate the final response in natural language. This architecture boosts factuality, enables domain-specific reasoning, and helps control hallucinations by grounding responses in retrieved content. Now let's talk about indexes and their role in retrieval-augmented generation. Think of the index as your AI's map to knowledge. Instead of brute force searching documents, we convert them into vector embeddings and store them in indexes. These power fast and relevant lookups based on similarity. AI models can't process entire books, so we chunk data, that is organizing the data in smaller pieces. Choosing how to chunk affects recall and relevance. For example, fixed length chunks are easy, but semantic chunking, that is splitting at logical boundaries, often improves retrieval quality. When we say embeddings turn text into vectors, we mean this literally. For example, the sentence "Paris is the capital of France" might be transformed by an embedding model into something like this. This is a high-dimensional vector. Note that different embedding models support different numbers of dimensions. What's important is not the individual numbers, but their position in the overall semantic space. A similar sentence like "France's capital is Paris" will produce a vector that's very close to this one. That's what enables smart retrieval based on meaning, not just keywords. This retrieval is known as semantic search. As mentioned before, when a query hits the system, it's embedded and compared with pre-indexed vectors. The most similar ones are retrieved as candidates. The speed and accuracy of this step hinges on how the index is built. Initial retrieval is fast but can be shallow. That's why RAG pipelines often include re-ranking, that is a second pass where retrieved chunks are scored in context of the query using deeper models or relevance signals. After ranking, we select the most relevant context and construct a prompt for the language model along with passing the retrieved context from the vector store. To this end, this prompt often combines instructions, the user's query, and the top-end retrieved chunks. Every step, from chunking to indexing to prompt formulation, impacts performance. To this end, it's important to take into consideration when designing RAG pipelines that using state-of-the-art embedding models, thoughtful chunk sizes, smart re-ranking, and clear prompts elevates the entire RAG pipeline. In RAG, the quality of generation depends on the quality of retrieval. By understanding and optimizing indexes, embeddings, chunking strategies, and ranking, we can make LLMs far more reliable and domain adapted. Thank you for watching this lecture. I hope you found the subject as exciting as I did. For more insights on AI, data, and other tech trends, subscribe to my channel on YouTube.